This video deals with a new concept which serves to answer a question that some of you may have had at the end of the previous video, which is like, okay, fine, extracting subgroup information is good, but how do I actually get that information? It seems like in practice, most of the time what's happening is you're giving me a homework problem that tells me something about subgroups and then I can use it. Where do I get that information from myself if I have a group? That's a good question. And so I wanted to include this problem to help start to answer that. It's not going to fully answer it because, there's a lot of different types of groups out there and you got to work with what you got. And until you start using groups in your life, there's no way that I can give you a comprehensive answer to this question. But I can tell you one source of subgroups that's really common throughout the rest of math. And so to understand that, we need to talk about group actions. So a group action is a function which takes in an element both of a group and of a set. Maybe we call this F, and it gives out another set element. And oftentimes we won't refer to F specifically. We usually just write G dot X. For normal group multiplication, when we've been using multiplicative notation, we don't write anything at all. We just write, GH or whatever, right? Concatenation notation for multiplication. For group actions, we often specifically use the dot to indicate that something a little bit non-standard is going on. And this then gives some other element of X back out, right? This is a function which takes in a group element and a set element and returns a set element. And we're going to require for our group actions that the group act on X in a way that remembers, if you will, that it is in fact a group. In other words, E dot X has to be X for every X. The identity element acts by doing nothing. We have to have G dot X, this is a set element now, dot H equals HG dot X. In other words, when a multiplication in the group, you can act one at a time, or you can calculate the product and then get the answer. Under these conditions, this is first off, this is what we call a group action. When we have a group action, then we can speak of two things. The orbit of an element, which is the set of all G dot X. Maybe we write this as O of X for the orbit of X. Sorry, that does not look like a set membership. It looks like a little G. And we can speak of the stabilizer of an element, which is usually called stab X, which is the set of G in G such that G dot X equals X. So first thing that I want to call your attention to is this is very much like the stuff that we were talking about in these last couple of chapters, right? This is very similar to a coset. The only difference is that the X's don't live in G, right? X is the thing being acted upon. And the stabilizer, this is going to be our source of group information. So the question in Pinter is a little bit lower level of generality. They focus on the case where the group acts on itself via multiplication in the way that we saw, or even more specifically, just focusing on permutation groups, where the action is G is a subgroup of some SX, and then by specifically writing them down as permutation elements, the action on X is by permutation. You can always reduce to this case For example, using Cayley's theorem, well, I guess maybe not. I shouldn't say you can always reduce to this case because x could appear in x could be some big complicated set like in geometry where it doesn't matter, not important. It's a tangent. Many such cases reduce to this case when groups act on themselves or on finite sets, but it doesn't have to be this way. Anyway, for the purpose of the exercise is to see that the stabilizer of X is always a subgroup. And so in this way, we now acquire a systematic source of new subgroups, because the only way we've seen of cooking up subgroups so far is when you have a specific element or maybe a couple of elements and you want the subgroup generated by those elements. Well, for subgroups generated by one element, those are cyclic groups. Subgroups generated by two or more elements can already be really, really complicated, as we've seen some interesting non-abelian groups. And so, we talked about transpositions, for example, and how every element of the symmetric group can be written as products that way. As such, it can feel daunting to come up with reasonable subgroups. This gives us a new way of searching for subgroups. Anyway, this is a lot of prelude at this point. I've already been talking for over 5 minutes. Let's actually check that this is a subgroup. So what we have to do is we have to see that the identity belongs to stab X. We need to see it's closed under the group operation. And we need to see that inverses are present. All right, one by one, E dot X is X by the first rule for group actions. And so, of course, E belongs to stab X. For closure, suppose that G and H are individually in stab X. Then G dot X equals X, and also H dot X equals X. But then GH dot X is equal to G dot H dot X by rule number 2. H dot X is X, and G dot X is X. So GH dot X equals X. GH is in stab X. All right, the last thing that we need to do is we need to see that if G is in stab X, then G inverse is in stab X. And why should this be true? Well, let's see. We know that G is acting by permutations. Right? This is required. And so if G is permuting elements of X, then G inverse is the inverse permutation. And so, well, if this permutation fixes X, then the inverse function fixes X as well. And we're done.